Welcome everyone to a new session of our series of webinars on data science and statistics, DaSSWeb. Today we have the pleasure of welcoming Karol Horn. Karol is professor at Palack University in Olomouc, Czech Republic, and is currently the head of the Department of Mathematical Analysis and Applications in Mathematics. His research is focused on statistical analysis of relative, that is to say, distributional data, both in multivariate form as compositional data or functional form as probability density functions, and is interested in applications in several areas as geochemistry, chemometrics, health sciences, and beyond. Through this work, he has published quite a lot of papers in reference journals and also a book. And of course, he has presented many invited talks and seminars in conferences worldwide. Karol Horn is an active member of the International Association of Statistical Computing, IASC, where he has served already 2 terms in the board of directors of the European Regional Section, and is a member of the executive committee, being the publication officer for 2 terms. Last year, he has been awarded elected member of the International Statistical Institute. Karol, it's really a pleasure to have you at DaSSWeb. Thank you very much for accepting our invitation, and we look forward to hearing about your recent work on density data analysis. The floor is yours.
Thank you, Paula. So at first, I would also like to thank you and Maria Eduarda for your nice invitation. And yes, I am going to talk today about density data analysis. So using the Bayes methodology. So brief outline of my talk. At first, I will tell you something about Bayes spaces in general and why it is appropriate to embed densities here. Then we will proceed to exploratory density data analysis because, of course, we cannot cover everything now in these 30 or 40 minutes. And as a specific instance, I will talk a bit more about so-called visual function principal component analysis. So how to reduce dimensionality of densities in a meaningful way. And then we will also proceed to simulate it in empirical data to demonstrate how the procedure works there. And finally, of course, there will be also some outlook beyond dimensional reduction. So I will start with empirical example. Here we considered age distributions of men and women living in 114 municipalities of Upper Austria. They can be represented as histogram data, as so-called population pyramids, but essentially these data are continuous. So finally, these distributions can be represented as probability density functions. You can see the data for both females and males. And yeah, in particular, you can see, or it seems that there's quite a variability in the left tail, a bit less variability in the right tail, which somehow reflects the initial view on density data we all know. So, and what we would like to do is to describe the variability of this data and also to perform a kind of dimensionality reduction. This is what we know in case of multivariate data with principal component analysis. And now we would like also to extend this to distribution data to densities. So this will be, say, the main target of our talk today. But on the way, I would like to also talk a bit more general about statistical processing of densities in base spaces. Okay, so this was first example. There will be also another example with income distributions. Here we have income distributions in all 20 Italian regions, which come from aggregation of the raw income data. And we would like to see in particular here some regional patterns, like some differences between North Italy and South Italy, and how also the middle Italian regions fit in this data structure. Okay, so I mentioned that densities result often from aggregation of raw data, and there is increasing necessity of having appropriate tools for processing of distributional data, because we have many large-scale data which we somehow naturally want to aggregate, but still while keeping their internal variation and structure. So I mentioned age distributions, but we can also have, in addition to those income distributions, for example, anthropometric distributions, particle size distributions in geology, concentration distributions in chemometrics, some omics data distributions, for example, metabolite distributions, and many others you can imagine from your expertise. Accordingly, densities can be considered as functional data, some specific functional data, which are characterized by two essential properties, which are called scaling invariance and also relative scale. I will say more details very soon in the next slide. But in any case, the integral constraint, so we know that the density is integrate to 1, somehow mimics the case of compositional data if we consider compositional data as multivariate observations which have the unit sum constraint. And there was quite a lot of done already about compositional data processing using the log ratio methodology, which is developed since 80s of 20th century, and nowadays it is characterized by the Aitchison geometry on the simplex with the Euclidean vector space structure, and we can develop coordinates and analyze composition data directly in real coordinates. But well, in our case, we have functional data, which on one hand can be considered as infinite dimensional extension of compositional data. But of course, there are some specific issues. And of course, we can also consider more general ideas than it would possible with compositional data. So what is the scale invariance I was talking about? So the usual integral constraint leads in our case to representation within a class of functions which provide the same kind of information. In fact, this is the usual probabilistic representation. But from Bayesian statistics, we also know about proportionality of densities. So in fact, we can consider the whole equivalence class of functions which are proportional to the density function in the usual probabilistic sense. So in fact, the sample space of densities is formed by these equivalence classes of proportional functions. Accordingly, because this is to some extent a consequence, we have also the relative scale property. So that in fact small function values of densities, or in other words relative likelihood, form here the main source of variability. And now we would like to take both these scale invariants and relative scale properties into account. Also including this specific sample space, which is composed by these equivalence classes. However, this is not possible if we would consider densities as the usual unconstrained real function data. For their purpose, the functional data analysis was developed. It is nowadays based commonly on geometry of L2 Hilbert spaces. And of course, they work well for known examples like growth curves or some temperature data and many other applications. However, when we are interested rather in the relative information, in the relative structure of data, what is the case of densities, we would like to have, or we need also to have some reasonable alternative. And this alternative is provided by Bayes spaces, which, as we will see in a while, have again Hilbert space structure. And if we consider a square integrable logarithm, we could also introduce in the product and indeed complete this Hilbert structure and also provide some isometric isomorphism with the L2 space. So just briefly, I don't want to go much details here into some formulas, but I would like to set the common setting, which is the compact support, usually an interval, and on this interval with the Lebesgue reference measure, and we could even consider other reference measures, but Lebesgue is the usual one. We consider operations of perturbation and powering. These operations are defined instead of the usual sum of two functions and multiplication of a function by a scalar. And we can quite clearly see that now instead of sum of two functions, we have multiplication. So we have a product of two densities, and then there is this lower index B2, which indicates that the result can be arbitrarily scaled. So we can rescale it again, for example, to unit integral constraint, our popular representation of densities, of course without loss of information, because we are in the same equivalence class. Similar with powering, so with our, say, multiplication of a scalar, but now we have this power to alpha, where alpha is any real number. And consequently, we can proceed to in the product between two densities with respect to Lebesgue reference, or we can also refer to lambda densities. Here we can clearly see in the integral that we have a log ratio between two function values of the first and the second density, respectively, which is quite a clear link to the log ratio methodology of compositional data. Here in the product, we would again consider log ratios between components of a composition, the first and the second one. So why perturbation and powering is indeed useful or meaningful for densities? It is in particular about the possibility of rescaling, because if we would simply consider sum of two densities, the resulting function would definitely not have a unit integral constraint. But in this case, it would be not possible to simply rescale. We are working with real functions. Why to do that? And similarly also with powering. So consequently, perturbation and powering together with the inner product, which we also called base inner product, form together Hilbert space structure of the base space. And we can then also proceed to some isometric isomorphism with the L2 space. Because on one hand, it is completely meaningful to analyze densities directly in the base space, because densities are well characterized there. But still, if we would resort to popular methods of functional data analysis, it somehow makes sense to proceed to the L2 space. And for this purpose, we have so-called central log ratio transformation, which is, as you can see, log transform density, where a kind of mean is subtracted. And the resulting function is a real function. There is just one additional constraint which we need to take into account. This is the zero integral constraint, which, however, doesn't represent any major obstacle for majority of methods of functional data analysis. And what is important, if we apply CLR transformation, we move the operations from perturbation and powering to the usual sum of two real functions, multiplication of a function by a scalar, and also to the usual L2 in the product. So exactly as what we would expect for the L2 space. So we can avoid computations directly in the base space on one hand, and still to keep some important properties of base spaces. Because what I would like to convince you in the sequel, in case of functional principal component analysis, working in base spaces is not just about applying some transformation, but also enjoy some additional theoretical properties of base spaces. But first, let's start with the usual descriptive statistics as a recapitulation for those who are not that much familiar with functional data analysis. So like for any real functions or for a sample of real functions, we can consider a sample mean, which in our case will be expressed in operations of perturbation and powering, but equivalently, we can also apply CLR transformation, so that we have CLR transform functions. For those, we compute the usual sample mean and then back transform to the original space. Back transform mean means by applying the exponential, and eventually rescale as we want or not. While sample mean could be defined directly in the base space, for the covariance structure, we prefer to work directly in the CLR space. And here we can consider the usual sample covariance function, which can be then visualized as a function of two variables, of course, for pre-smoothed CLR transform densities. This is also an important point because, as it is usual in functional data analysis, we want first somehow to smooth our data using some basis expansion and then to proceed with the analysis. So we have our anthropometric densities again, and what you can see, these are the original densities together with mean functions, and on the right there are the same functions but in the CLR space. And now we can see something a bit surprising, and that the main variability or main source variability is now in the right tail. Which is somehow maybe intuitive, because here we can see the main differences concerning those regions in terms of life expectancy. In fact, this is information which is quite useful for us for distinguishing the districts into those with higher life expectancy and vice versa. We can also see that these values of the domain with high age form the main source of variability in the respective covariance function for both males and females. So let's proceed to dimension reduction now. And first, let's recap again a bit functional principal component and directly to statistical processing of densities. So let's consider centered functional random sample. So we subtract the mean from all observations, and then functional principal component analysis looks firstly for the main mode of variability, so some element in the L2 space, which is called the first functional principal component, where we maximize this term over all possible functions in the L2 space, of course, somehow normed, so that this maximization task has sense. And the aim is to capture the domain modes of variability of the data by means of just a small number of linear combinations of the original variables. So in this sense, so that we also produce some new coordinates, which are called scores in this context. Of course, when we have the first functional principal component, we can also proceed to remaining modes of variability, subject that we want them to be mutually orthogonal. So this basis representation, so to say, is an orthogonal or even orthonormal representation, because these functional principal components, or we call them also harmonics, are mutually orthogonal. Okay, so we have these harmonics or eigenfunctions. We also call them. They are interpreted in terms of the original data, but also scores, which are coefficients of this linear combination of harmonics. And coefficients represent an data structure of the original observations. And eigenfunctions as I mentioned previously, the main modes of variability. So going into a bit more detail, just to mention that functional principal component analysis is indeed analogous to multivariate principal component analysis. So the functional principal components coincides with eigenfunctions of the sample covering operator defined here, and we also then consider the associate scores as in the product of the sample entities, or here real functions with these eigenfunctions, which are obtained by solving the eigenvalue equation. As for any eigenvalue equation in the multivariate sense, we also consider eigenvalues, which are ordered in decreasing order. So, and using these eigenvalues, we can assess the proportion of explained total variability by the respective functional principal components. But because we have now functions and not multivariate data, we need first to represent our functional observations using some known basis functions. Say we use some k known basis functions. And for this purpose, we commonly use smoothing splines. So this was just briefly about functional principal component analysis, and now how to reformulate it in terms of base spaces. So at first sight, it's quite simple. We simply use, instead of operations of sum of two functions and multiplication by a scalar, the respective operations in the base space. Accordingly, also the maximization problem is formulated in terms of base spaces. And if we want to efficiently implement all this, the easiest way is now to apply the CLR transformation. And essentially, one could say that it's it. Just there is one consequence of functional principal component analysis in the CLR space, that we have additionally this constant function which corresponds to this zero integral constraint. Of course, this zero integral constraint needs to be incorporated also in the basis expansion, which results in so-called compositional splines, which again I will introduce a bit later. Right now. So because compositional splines are or can be considered as the usual B-splines, just that the basis functions honor the zero integral constraint. So instead of usual B-spline basis, we consider basis functions which all have zero integral constraint, and then we can construct the usual splines with knots, as what we know from the standard spline theory. So for example, here we have some particle size distributions. We can see that there is not much variability visible here in the tails. However, this is just in the original space, but in the CLR space, where we first transform the raw data, say usually the raw histogram data, because we collect our data in terms of histograms, we have then representative values of those classes and proportions corresponding to histogram classes, then we would use the discrete CLR transformation, and we arrive to the CLR space where we smooth these discretized data using, again, functions which honor the zero integral constraint, and in our case, using lines which honor this zero integral constraint, or using their basis functions. Now we can clearly see there's quite a lot of variability in both these tails, which would be completely ignored if we would analyze densities directly in the original space by ignoring some base spaces. Okay, so here we can see the spline basis functions, here B-splines, and here so-called ZB splines. So this means basis functions which already honor the zero integral constraint. We can see that according to variability in data, we can select also not, so that of course the basis accommodate accordingly. But let's come back to our dimensional reduction, and let's introduce some data which we will use for simulations. And here, as you can see, this is nothing else than normal densities with zero mean value and some increasing values of spread, which can be, of course, represented in the original space, but also in the CLR space. And in the CLR space, we can see once again the same effect which we could observe before, so that in tails, or that tails are in fact the main source of variability. Of course, still in the middle of the domain, we can quite large portion of variability see again, but now it's not the only source of variability. What is maybe even more important is that normal densities belong to so-called extended exponential family, like also many other densities, both well, the usual continuous densities like gamma distribution or log normal distribution, but of course also discrete distributions, including binomial and Poisson distributions. So all these distributions can be expressed as a specific instance of this very general form, where we consider for k parametric extended exponential family k-dimensional vector of parameters in a k-dimensional parameter space A. Okay, so what is important in our context then is that an extended exponential family on omega, so on the domain, is a finite dimensional affine subspace of the B space, of the base space. So it means that while in general, of course, base space is infinite dimensional, if we consider densities coming from the expansional family, we can represent them in a finite dimensional subspace. So like here, when we have our Gaussian densities, we considered one parameter to be variable. So in fact, we have one parametric extended exponential family. And we do not need to proceed directly in the base space, but we can also use the CLR transformation and then analyze again densities as real functions. But by keeping in mind that they live infinite dimensional subspace of the base space. So if we would perform normal or if we would perform functional principal component analysis for these normal densities, we can clearly see that we have just one functional principal component which explains 100% of variability. That's fine. And we can see also the respective eigenfunction, so that there is a kind of contrast between the positive values on tails and negative values in the middle of the domain, which nicely reflects the main mode of variability. Of course, the second harmonic is just a noise. So in other words, we are able to reconstruct these normal densities just with one function principal component. Similarly, we could, for example, consider gamma densities, again truncated on this domain. Now with two parameters, so we have two parametric family. So accordingly, we can expect that our dimension reduction will be represented just by two non-zero eigenfunctions, reflecting the main sources of variability, so that the original densities can be reconstructed by these two functional principal components with, say, 100% explained variability. So this representation of exponential densities or densities coming from the exponential families can be then useful model where we assume as the underlying true densities densities coming from this parametric family, which in case of dimensional reduction can now be very useful because we can guess and clearly estimate the number of components needed for representation of the densities. If we would ignore any base spaces and would proceed directly with functional PCA of here of the gamma densities, we would obtain some nonlinear pattern as expected. Of course, also the harmonics would look quite differently. And if you would like to reconstruct the original densities, of course, something like that can happen, that we would have even negative values of densities. So let's come back to our population age distributions. We were focusing on the right figure, so densities in the CLR space, because they are of interest for processing usual functional principal components. And we can also see the respective harmonics in this original space and in the CLR space differ quite substantially. So while here we have more sources of variability or apparent sources of variability in the CLR space, you can clearly see the main source in the right tail. That's for the first simplicial functional principal component. Also for the second one, although the information on variability is more diverse here, here we can also observe some pattern in the left tail, which was anyway present in data. We could also display scores, and we can clearly see that females live longer. Of course, the scores can be also plotted directly with the original region data to see some regional patterns, like also for income distribution, where we somehow expected this. So we expected that there will be a cluster of North Italian regions versus South Italian regions, and the Middle Italian will be somewhere in the middle. Again, the main source of variability is somehow concentrated here in the left tail, which distinguishes mainly the poor regions, because in the left part of the domain we can see the lower income classes. Of course, we now do not have simulated data, so we cannot expect that all variability will be explained by the first component, but still quite a reasonable portion was explained by the first functional principal component. You can also use the R code related to this story. So you will have also these slides available. So then you can simply click on this link, and you will get not just codes related to dimension reduction, but also to other methods which are developed in base spaces and currently implemented in R. So now I'm going already beyond dimension reduction, because of course base spaces can be used for any statistical processing of densities, using methods of functional data analysis, but also beyond again. We can consider, for example, functional regression, specifically density on scalar on density, and density on density regression. We can also perform classification, outlier detection, and, for example, change point analysis. For 3 years, there is quite an explosion of new methods and papers. So you are invited to explore internet, what is already available. Or of course, I'm also here, and you can contact me for possible questions. This all was about univariate densities. Of course, now we can also proceed to the multivariate case. So we can first extend the story of densities in base spaces to the bivariate case, and also to the general multivariate case. And if we would do that, we can also enjoy orthogonal decomposition of multivariate densities into independent and interaction parts. So this is a bit, say, more complex story. So for another talk. But what is the important message is that such orthogonal decomposition exists, which doesn't have counterpart in the usual methods, which are somehow used for analyzing multivariate densities. So that's something new, quite a recent developments were done in this direction, including already some first steps in functional data analysis of multivariate densities. Of course, related to this, we now also need multivariate spline representation, which is currently also under development. And this is still not all. There is also a great potential of Bayes spaces in Bayesian inference. I mentioned Bayesian methods at the very beginning. In fact, also the operation of perturbation can be considered as a Bayes space representation of Bayes theorem. So then the Bayes theorem is merely just a shift. Of course, very important shift in statistics. We can also consider Bayes spaces in graphical models for modeling conditional distributions and many other applications can also be developed. So, and finally, some references related directly to this talk, to statistical analysis of PDFs in general, and also to multivariate Bayes spaces. So that's all from my side.